Very good evening, everyone. Good evening, everyone. I welcome you all for today's physical pharmacy class. Good evening. So today we are going to cover our micromeretic section. So you all must know this thing that micromeretics, yes, it does play an important role mainly in not only in GPAT but in all pharma related exams. All right, let's wait for a few others to join and then let's start with our topic. Yes, good evening. Few of you have joined. So basically what we are going to do in this series is to introduce you all to the newer concepts. Most of you I think will be from the final year or third year students, or even better if you are from second year, right? So we are going to prepare you all, introduce you all to the topics which are highly important from the GPAT point of view as well as other pharmacist exams as well, right? So you have seen the trend, right? You have seen how the questions are continuously from these chapters only. So this is one among the most important your topic for the GPAT preparation. So understanding the basics, attempting few questions is very important, right? So let's start. Let's not waste any more time. So the key of these batch include that we are going to offer you around 500 plus live classes. Obviously the faculties are all specialized in the subject. We will be providing you with the previous year papers, the hard copy books, the 500 daily practice papers. You will be getting online test series with the planned series, chapters, daily practice papers, etc. you will be getting, right? Not only this time you are also going to get important e-notes for the BPharm and GPAT, right? So for that, first step you have to download the GDC app from the Play Store. Then you have to click on the batches section, right? And then you have to enter this batch code. Remember this, right? So all these are provided based on your requirements, based on your subject, based on how it is planned, based on your GPAT and B pharmacy syllabus or that included, right? So we are here for you all so that you can prepare well and perform well. Not only performance in the exam, but being a pharma student, you have to be consistently introduced and remember these topics like very concisely, right? So one suggestion from my side, after today's lecture, if you are a final year student, third year student, even second year student, make sure to revise what I have taught, because in the upcoming video I will definitely connect these points. Okay, so what is the whole point of studying physical pharmacy? First thing first, what is the whole point that stands with this subject, physical pharmacy? See, yeah, the pharmacy does not only include studying the drugs, studying the drugs types, their mechanism of action, their side effects, but it is also a novel profession where studying how the drug is going to function and how you can make it perform even better, right? It's not just the traditional drug, but you can repurpose the drug. You can introduce the drug into a novel systems so that the efficacy of the treatment improves. The ultimate goal is to improve the patient last like patient outcome, right? Whatever the suffering is, it should be cured, and whatever the therapeutic outcome is, it should improve, right? So to in order to improve that, we have to troubleshoot into back step. What is the side effect, whatever is the mechanism, what was the action, how was the drug performing, what was the route of administration. But even before that includes the designing, right? So while designing a formulation, you have to keep a lot of things in mind. One of those is included in the physical pharmacy, where you are going to study how the drug or the material is going to behave, and that impact will be definitely be seen in the final therapeutic outcome. So all the dots will be connected. For example, Today we are going to start with the micromeritics. All the important points I will cover. Just keep your ears open. Micromeritics. Micro means what? Means small in size. Micro means small in size. So study of smaller particles. Why we are studying smaller particle? What is the advantage that is offered using such smaller particles? So once the particle is small, definitely its release, its dissolution is going to improve. Number second, if the dissolution is going to improve, the absorption will be improved. If the absorption improved, that means the stability of the formulation is also improved. Now, once you can spot the physical stability, not only that, we are also talking about the storage stability, the chemical stability. The stability itself is a challenge while you are dealing with such smaller particles. I'll give you an example. Before going into the chapter, I am going to explain you a little bit how these are going to perform. Okay. So those who are connected with me right now, please pay attention because this is definitely going to help you a lot, right? So if you have suppose a smaller particle and a larger particle, you have a smaller particle and a larger particle. We have seen that the smaller particles offer better dissolution. If the dissolution is better, definitely dissolution is better, the absorption will improve. Absorption will improve, the final action is going to improve. Action will improve, the therapeutic outcome will improve. Therapeutic outcome improves, patient is all fit, right? So this is how we have to spot that what exactly it is going to offer. I will give you one simple example which will clear all your doubts regarding how these smaller particles actually behave. See, this is the example I have given last year also. For example, this is a tumor tissue. Let's take an example. This is a tumor tissue. You all know about the cancer, right? So the tumor tissue itself is very difficult to handle, right? It is very difficult to detect as well as to invade. That is why most of the chemotherapeutics that we give for the tumor treatment usually end up into the failure. What is the reason? Number one, they cause systemic toxicity. Number two, they are directly exposed into the blood, which will definitely lead to the toxicity, right? Second is the tumor tissue has a lot of PGPs. If you remember, they are going to throw them out. So what we have in option? If we reduce the particle size, obviously we cannot reduce the particle size of the drug, but we can load the reduced particle size into a carrier system. We can reduce the particle size and load it into a carrier system. And now if we use the tumor tissue physiology, we can see there in the blood vessels where you have tumor tissue, there are smaller gaps here. So the particles smaller in size take the advantages of such gaps and invade the tumor tissue. So this way you have reduced the dose, you have reduced the toxicity, you have improved the overall efficacy, right? Which was not possible using traditional chemotherapeutics. So you have seen how just reducing the particle size improves the overall outcome. So that is why understanding the particle behavior is very, very important. And all this is what we learn in the physical pharmacy. Right? So now let's come back to the point as mentioned. If the particle size is going to improve, the release is going to improve, the dissolution is going to improve, the absorption is going to improve, the action is going to improve, the overall therapeutic outcome is going to improve, and the ultimate goal is the patient compliance, which is going to improve. Okay, so I hope now you have a small idea how the particles actually function. You can just use them and you can modify their functioning, you can modify their efficacy just by formulating them, just by reducing their size. That will increase their effective surface area. Okay, I will repeat the same points again and again for you. So how does the particle size is even determined, right? How is the particle size even determined? You all know. Basic technique. This is most important from GPAT exam point of view. Basic technique is optical microscopy. You see, whatever you see, you have least count methods here. You have micrometer, stage micrometer. You can read how many counts will be done and you can estimate the particle size. But this method using the optical microscopy is a very slow method. It will take a lot of time. Sometimes if the particles stick together, the counting gets very difficult. So the results are not much good, right? So for that reason, what we can see, we have alternative microscopy techniques. Number one, how you can determine the particle size. Number one is the microscopy method. Every time note it down today itself. One question from this table which I will show you right now. Methods of particle size determination in every test series, every PYQ questions you can spot, every series you will get, every time you can spot one question. So microscopy is just based on the traditional method. You have an eyepiece, you spot the particle from the eyepiece, you count the from the stage micrometer and you get the particle size. But definitely you will have an issue because here the particle counting is slow and estimation of depth is not much defined. Okay. Number two, very important, particle size in the range of 0.2 to 100 micrometer can be counted. But as I have mentioned, there are smaller limitations to better have the resolution of the particles. There are other techniques of the electronic microscopy. We have SEM, we have TEM, scanning electronic microscopy and transmission electron microscopy. Remembering their names is more than sufficient. Because of the traditional issues in the optical microscope, we have the electronic microscope. SEM, TEM to study the morphology as well as internal structure of the particle as well. Then we have a light microscope. Okay. Next, you can also spot there are multiple diameters that are written here also, right? The types of diameter are also mentioned here, which I will discuss later on. Okay. So one thing is clear, microscopy method 0.2 to 100 micrometer, but the problem is agglomerates, if the particles depth it cannot be estimated. Number second, we have electronic microscopy. For a better resolution, we have scanning electron microscopy. We have transmission electron microscopy. At the end of this lecture, if you are listening to me, you will get through it. You will learn it in the today's class only. Okay, I will revise it for you again and again. Next we have is the sieving method. You all have heard of the sieve. You have seen it in your labs. So here is a sieve shaker. Sieves are placed one above the other. That means the lowest one will have the finest particle and the topmost one will be having the coarse particle, right? Fine particle and coarse particle. So good evening. Some students have joined very late, but please pay attention. Microscopy is done. Sieving method, we have coarse particles above and then the fine particles below. So sieve are arranged based on their sieve numbers and diameters. That means the coarse particle will be the most on the topmost sieve and then we will get the fine particle as it reaches the bottom. And the diameter which we are going to see will be the sieve diameter. Device will be mechanical shaker. Although we have numerous sieves, the standards are already set, which is also important. We will see that. Okay. Important instruction is remembering the particle size. For the optical microscopy, it was 0.2 to 100 micrometer. For the sieving, we have 50 to 1500 micrometer. Very important. I am telling you, very important. Mark it 5-star today only. Okay. Next we have is the sedimentation method. I think it is the most important topic from the GPAT examination physical pharmacy subject point of view. If you ask me in the micrometers, this chart itself is very important. Okay. So sedimentation method, you can see how many times 𝑙𝙗𝑝𝑒𝑟, GPAT, 𝙂𝙂𝙗𝑝𝑒𝑟, GATE, you can see already how many times this question has been asked. So optical microscopy is done, you have counted the particles, you have faced the issue. Sieving is there. For sieving, you can ask me that, ma'am, how is the particle size estimated when we are talking about the sieving? See, you get the coarse particle, you get the fine particle. So we get the particle number, particle weight. So particle weight can be converted into particle number using a 𝙭-Couette equation. You get particles oversize and undersize. We get the particle weight. That particle weight can be converted into particle number, right? So using equation like 𝙭-Couette equation. That is why it is a method for particle size determination. Third, we have sedimentation, as the name suggests. So sedimentation is going to take place. That means the particles which are larger in size, we all know the particles which are larger in size are going to sediment faster, and the particles which are smaller in size are going to sediment later on. Okay, so that is why we have to see, even if the sediment is formed, if it forms a hard cake, that means not easy to redisperse, then we say the formulation is not good. But if the redispersibility is high, then we say this formulation is working fine. So whenever you will hear about sedimentation, remember three methods. We have the balance method. Here it is written balance method, hydrometer method and Anderson pipette method. Balance method, hydrometer method, Anderson pipette method. All these three methods are based on the sedimentation. That means rate of the settling of the particle, and most important among this is the Anderson pipette method. Okay. Size range for optical microscopy was what I had already mentioned, 0.2 to 100 micrometer. For sieving it was what, 50 to 1500 micrometer. For the sedimentation it is 1 to 200 micrometer, right? So this is an important information. Now let's focus on what else we should remember. Sedimentation method, three methods, which Anderson pipette, hydrometer, balance method, right? Size range 1 to 200 micrometer. Third thing, today itself in the dispensing you will learn, in every possible manner you will learn that sedimentation method is all based on a simple equation of Stokes law, right? I am telling you this equation today only. In all the classes it will be repeated. Stokes law equation. Now Stokes law equation is somewhat like this. Let's divide this and see what it explains. So Stokes law equation, number one, because it is a sedimentation method. Now because if the particle size is larger, that means diameter is big enough, then sedimentation will be quite faster, right? So based on this equation, this V is going to be velocity or the rate with which particle is going to settle. We can spot this is directly proportional to square of diameter. That means if the diameter is increased, the rate of settling will increase. Then you can spot 18 eta. That means the rate of the settling of particle is inversely proportional to the viscosity. Alright. So increasing the viscosity will reduce the rate of the settling of the particle. Then this is we have is the density difference. You can see V is the velocity of the particle of settling. G is the acceleration due to gravity. This R is going to be the droplet radius if you are going to put R, otherwise you can put the diameter. Then we have density of dispersed phase and dispersion medium. Okay. So what we have learned? Optical microscopy. Second we have learned sieving. Third we have seen sedimentation method. Okay. In the sedimentation method, never forget about the Stokes law equation. Last we have is the Coulter-Counter method. Last we have is the Coulter-Counter method. For the Coulter-Counter method, it is based on the conductivity. The size range will be 0.5 to 500 micrometer. Size range will be 0.5 to 500 micrometer. So the name of the instrument will be 𝘂𝙎𝙎𝙎𝙎𝙎𝙎𝙎𝙎𝙎𝙎𝙎𝙎, 𝘂𝙎𝙎𝙎𝙎𝙎𝙎, whatever, it is fine. So what is so special about this instrument? Now, all we have seen in the optical microscopy, the issue was agglomerates cannot be counted, depth of the particle cannot be estimated. So we use SEMTEM to get a better idea of the particle size, morphology and crystallinity or any nature you want to see. Then we have seen sieving method. In the sieving, coarse particles are above and then we get the much finer grade. Then we have to convert the particle weight into particle number. Third, we have seen sedimentation method, very important. Hydrometer, balance, Andreessen pipette method. In the Andreessen pipette, questions are asked. Next, we have seen is the Stokes diameter equation, Stokes law equation, which states the rate of the settling of particle is directly proportional to the square of diameter and inversely proportional to the viscosity. Last we have is the conductivity method. In the conductivity method, size range will be 0.5 to 500. Because it is based on the conductivity method, here we will have an orifice in this tube. You can spot a little orifice will be there. Obviously, these are connected to batteries. As soon as the particle passes through these small orifice, as soon as the particle passes through this little orifice, there will be a change in resistance that will be recorded. Mark my words. As soon as the particle passes through little orifice, there will be change in the electrical resistance. That change in the electrical resistance will be received as a signal of particle count, that how many particles have been counted. But in this case, we get a determination of particle volume. The final result we achieve is the particle volume. This method is so fast, it can measure up to 4000 particle per second. Right? Every word you see here is very important. Every word you spot here, right? So we have conductivity method. Conductivity method is based on the change of the electrical resistance once the particle passes through orifice. That change in resistance will be recorded as a signal. This signal will be interpreted as the final result will be the particle volume. Whatever you get, particle diameter, weight, number, count, volume, all can be converted into particle size, their diameters with specific equations. Okay. So then we have important, that is the size range 0.5 to 500 micrometer. The name of the instrument as well as measures the particle volume. Questions are asked. Which of the following? Okay, let's see how many of you are able to answer. I'll ask few questions based on this topic only. So let's first complete this Coulter-Counter method. You have seen it operates on what principle? When the particle passes through a small orifice, it will actually cause change in the electrical resistance. This change in the resistance will be noted as signal and the final result will be particle volume. Also, this is known as a stream scanning method or Coulter-Counter method. Very important. Okay. Now, let's see how many of you will be able to answer the questions that I am going to put now. Okay. Let's see which methods is based on determination of particle volume. First option is sedimentation. Second option is hydrometer. Third option is temp. Fourth option is Coulter-Counter. Let's see how many of you are able to answer this question quickly. I am waiting for your responses. How many of you are able to answer this question? Very simple question. Which method uses the end result is determination of the particle volume? Is it sedimentation, hydrometer method, temp method or Coulter-Counter method? Very good, very good. Right. So yes, correct. So we have already seen the Coulter counter method. Sedimentation method, it is a separate method. We have optical microscopy, sedimentation method. We have the Coulter counter method and sieving method. So sedimentation method is different, in which hydrometer, balance and Anderson pipette method is there. Then we have TEM, which is transmission electron microscopy, which is a thing we have seen in the microscopy technique. Then Coulter counter method is going to be the correct answer. Very correct. Right. Yes. So let's move ahead. Okay. So these are the sieves. You can see this is a perfect way you can spot how the sieves are actually arranged. This is a very coarse sieve. You can spot the diameter and you can see the powder grade as well. Then you have small diameter sieve. You can spot the particle diameter, particle grade as well. Then very fine. Then we have ultra fine sieve. These sieves are placed on a sieve shaker, which is going to actually reduce the particle size based on the impact and intrusion, because it is going to shake the particles, right? Okay. Next, these are the grades of the powder. We will cover this in the later stage, but I can just show you, because you should know that the grades of the sieves are arranged based on the grade of the powder. Number one is the coarse powder. You can see the number, the sieve through which all particles must pass will be 10. Then you have moderately coarse, we have 22. Then we have fine. As the sieve number is increasing, the particle is becoming more fine. So if you have a 60 sieve and you have a 20 sieve, you will get a more fine particle from a 60 sieve, right? So the sieve numbers are assigned based on the grade of the powder. Okay. Then in the sedimentation method, you have seen 1 to 200 micrometer size. You have seen Anderson pipette method, balance method, hydrometer method. Then you have seen that the only applicable equation will be the Stokes law equation, right? So this is the representation of an Anderson pipette. This requires additional attention. Then we are going to shift back to the nature of the particle and what are the particle properties we must focus on. So this is an example. You can clearly see this is an Anderson pipette. So Anderson pipette is based on which method? It is based on the, okay, you guys can tell me Anderson pipette is based on which method of determination? Number one, it is used in microscopy. Option B, is it used in the sieving? Option C, it is used in the sedimentation. Option D, it is used in the particle volume measurement. Let's see how many of you can answer. Where we have seen these particle determination using the Anderson pipette method, where we have seen. Let's see now you all can answer or not. Correct. So yes. So we have seen it in the sedimentation method. In the sedimentation method, you have seen Stokes law equation. You can see how many times I am repeating the same thing, because it is important. Once you will reach the end, you will see what is the pattern of the exam. You will spot same questions. At least note these now. Mark them star. Okay. So Stokes law equation was based on the rate of the settling of the particle. Velocity is V. We have diameter as d square. We have density difference rho s minus rho naught g upon 18 eta. Remember this equation over and over again. Right. So once the particle size will increase, the rate of the settling of the velocity will increase. Viscosity decreases, rate of the settling of particle decreases. Right? Increases, sorry. So then what are the important things to remember from an Anderson pipette? So this complete pipette, you can see we have a pipette inside here. You have a sampling reservoir here. You have a tap here. Then here is the upper and the lower limit. So please mark, this is completely a 10 ml Anderson pipette, right? It is a 10 ml Anderson pipette in which 550 ml is the capacity of the whole vessel. 550 ml is the capacity of the whole vessel. 10 ml is the sampling it can do at once, right? So you can be asked, the sampling is only 10 ml sample can be withdrawn from this at once. Whole capacity is 550 ml. Okay, that's it. No, you don't have to remember anything else. You have seen the Stokes law equation. So what exactly do we get later on? You get the particles, you weigh the particles. What you achieve from this sedimentation method, you dry the particles, you weigh the particles, you convert the particle weight into particle number. So that is how you get the particle number. You must complete this, I think, in your B.Pharm labs. You will see in the final year or maybe in third year. Okay. Then we have Coulter counter method. We have seen. So this Coulter counter method operates when the particles are suspended in a conducting liquid. For example, you can spot this will be a sodium chloride will be used as a conducting liquid. You can spot a little orifice here. So once the particles are going to pass through this orifice, it will record the signal. There will be change in resistance. This change in the resistance is recorded as a signal for the estimation of the particle volume. It is a stream scanning method. It can estimate up to 4000 particles per second. Such high and rapid estimation can be done. Okay. Then these are all about the particle volume. This is the complete diagram of the Coulter counter method. You can spot the electrolyte solution is supplied here. We have an orifice here. So this signal that is detected is converted into a major signal using this amplifier, and then you get the final result. Okay. Then most important thing that you have seen in the starting is the diameters which were mentioned in the optical microscopy method. So there are three diameters once you are talking about the optical microscopy method. Number one is the projected diameter. Number two is the Martin diameter. Number three is the ferret's diameter. I think in this GPAT exam also one question was asked from this, or in the NIPER this year only, like few days back only. So this is very important. Last 5 years continuous questions are coming from this topic. So you can spot projected area diameter. It is the diameter of a circle with the same area as of the particle observed, right? Martin diameter, length of the line bisecting the particle. Ferret's diameter, distance between two tangents on the opposite side. Okay, we have read what it says. Now let's understand what it actually means. So what exactly you see here is a diagram which is showing that we have a particle. See, very simply, we have a spherical particle here. Actually, this particle is assumed to be in a shape of spherical. You can have asymmetric particles. This is an asymmetric particle. You put this asymmetric particle to be in a shape of approximate sphere. That is why in the projected diameter, it is the diameter which is observed as the same area when viewed from a most stable plane. This stable plane is the tangent plane only, right? So projected area diameter focuses because we assume that this particle, asymmetric one, is approximately similar to the shape of the sphere. Next, you have ferret diameter. Just remember two words, FT, MB. FT, MB. You already know about the MB, GB, TB, right? So FT, MB means F says ferret, T states tangent. F says ferret, T says tangents. M says Martin, B says bisect. FTMB, FTMB, FTMB. Just revise it like 1 or 2 times. It is done. FTMB, FTMB. Ferret's tangent. Martin's bisecting the line. See, you have already seen the projected diameter. Let's spot the ferret's diameter. So, as mentioned, ferret is the tangent, stands with the tangent. That means, now let's see. Now I think it is clear. So, ferret's diameter is the distance between two tangents. Ferret's diameter is the distance between two tangents. You can see the particle ending here. So it is the distance between two tangent FT. Then you have seen MB, Martin's diameter, which is the length of the line bisecting the particle. Length of the line bisecting the particle. Very easy to spot. Projected diameter was having the similar area. When viewed from the stable plane, you can spot here. FT, ferrets, is the distance between two tangents of the particle. Martin will be length of the line bisecting the particle, right? So now let's read what it says. Projected area diameter. It is the diameter of a circle which is the considered to be in a shape of sphere having same area when they both are actually compared, right? When observed with the similar surface area. Then Martin diameter, FT, ferret, FT, Martin, MB. Length of the line bisecting the particle, MB. Ferret's diameter, distance between two tangent, FT it is, distance between two tangents. I hope it is now clear to you all. Okay, so by far you have covered what exactly you are going to see. We are going to learn more and more about the nature of the particle, right? So basically, we can divide the powder properties. We can divide the powder properties into two types: fundamental and derived. Fundamental and derived. Fundamental properties include particle size, particle shape, particle surface area, right? So particle size, shape, number, all these are fundamental properties. From these fundamental properties, we can derive the properties which are known as derived properties. For example, we can derive density, we can derive volume, we can derive particle density, it is, volume it is, then we can derive porosity, that means void volume, flowability, nature of the particle flow, right? Then we have bulkiness. Once you will read about the density, you will understand. So all these derived properties are derived from these fundamentals. Fundamentals of powder properties including the size, shape, surface area, number. So today we have learned about the particle size, particle number, particle shape from these diameters, particle number, that size can be converted to and fro from weight, and then we have seen particle size determination methods. Which methods we have seen? We have seen the, let's revise quickly and then move ahead. So we have seen the properties of powder. I have just mentioned we have the derived properties, we have the fundamental properties. Particle size, particle distribution, shape, surface area, weight, number. These are fundamental properties. Derived properties includes density, porosity, bulkiness and flow properties of the powder. Okay. Let's see how many of you can answer this question. Just to revise what we have covered, and then we are going to move ahead very quickly. Okay. So first question, the instrument used for measuring the volume of the particle, we have covered it today: hydrometer, balance, Anderson pipette or Coulter counter method. Let's see how many of you will answer this question. This is a very simple question, huh? Very simple. Right, because we have seen that the hydrometer, balance and these Anderson pipette method, these were a part of the sedimentation method, in which law we have seen? we have seen the Stokes law equation. I will repeat it over and over again till the time you remember the equation from today's class itself. If you just remember it 1%, write it with me. What is this Stokes law equation? It is V is equals to d square rho s minus rho naught g upon 18 eta. Okay, this Coulter-Counter method is the method used for the determination of the particle volume based on the determination change in the resistance occur, which is noted, and finally 4000 particle per second can be counted. Okay, we have seen this is a very good summary. Microscopy size 0.2 to 200, sieving 50 to 1500, sedimentation 1 to 200, conductivity, that is particle volume, 0.5 to 500 microns, right? Instrument was optical microscopy, sieving, mechanical shaker. Then we have Anderson pipette method, and then we have Coulter-Counter Rheology or HIAC, right? Next question. The question is little bit bigger. Let's see how many of you can answer this without my help. I'll read the question for you. In Coulter-Counter method, as the particles move through the orifice, the event that occurs is option A, conductance between the electrodes increases. Option B, electronic scanners produce photographs for volume measurement. Option C, resistance between the electrode increases, and option D is sedimentation increases. Let's see. One student has already answered very correct. He has been answering the question like 5. I have seen his response is nice. Pooja says C, right, correct. One more request from my side to you. If you enjoyed this lecture, if you understood what I have taught you today, I would really like to see all of your comments post my lecture on this video, which will let the confidence be present in me as well that you all have studied it well. It has definitely improved your knowledge from the start. And let's come back to the question. Yes, the Coulter-Counter method, definitely. This method, the particles will move through the orifice, which will cause change in the resistance that are going to increase the resistance, and it is noted as a signal which is recorded as a particle volume. Okay, many times you will spot this question. Okay. Then we have seen that the methods are for the particle size determination. Now there are two more methods based on the particle surface area determination, right? Particle surface area determination can be made using two methods. Number one is the adsorption method. One question was in GPAT 24, two questions in 25 from this topic only. Then we have is the air permeability method. Number one is the adsorption method. Second one is the air permeability method. Adsorption method means something is going to adsorb, not absorb. Adsorb, where? Over the surface of the particle, whose surface area you are going to determine. Okay. So, adsorption method includes adsorption of either solute or gas, which can be adsorbed over the surface of the particle. Now, the amount of the solute or gas that is adsorbed can be counted, and thus from that equation you can put and get the correct answer for the surface area. But for now, remember, for the adsorption method, the solute or gas can be adsorbed over the surface of the particle. Now, once the solute or gas is adsorbed, this can be done using an instrument named as QuantaSorb. Right? Very important. Mark it 5-star today only. Okay. Number one is the adsorption, gas or solute. the particle, the solute or gas can be adsorbed over the particle. Now, this is going to resolve through an equation we call as the BET equation. We call as the BET equation. That is why Stokes law equation I repeated over and over and over and again, because these equations are highly important from your exam point of view. Okay. Then, in the air permeability method, name suggests air permeability. Here we have a packing like this in which smaller capillaries are kept. In these small capillaries, we have our powders that are stuffed in these capillaries, and above which the air is actually passed. Obviously, you will get a more idea of the porosity here. Porosity means voids, holes, gaps, right? So we get an idea of the powder packing in this case. So the air is passed, so the gaps between the particles can be really estimated. For this reason, you can get the 𝙂𝙂𝙎𝙬 equation. 𝙂𝙂𝙎𝙬 equation GPAT 2025 question. 𝙂𝙂𝙎𝙬 equation, right? So you have seen number one is the adsorption method, for which the solute or gas can be adsorbed over the particle, right? The instrument is QuantaSorb. Then BET equation is generally applied to calculate the surface area. We will see what is the BET equation. Then we have is the air permeability method. In the air permeability method, there are series of capillaries in which the powder is packed. Which powder of which the surface area is to be determined. Then the air is passed and the estimation of the gaps and the surface area is made using 𝙂𝙂𝙎𝙬 equation. Okay, so this is what we have learned so far. Number one is the surface area determination using the adsorption method, in which volume of the gas or the solute that will be adsorbed over the particle surface, of which the surface area is determined. Initially, monolayer is formed. Initially, monolayer, that means single layer is formed. Above then, once you keep on passing the particle in, once you keep on supplying the gas or the solute, it will form the multi-layer, or it depends on the nature of the particle. If it is porous, then it can start multi-layer formation itself. We will study that in the surface tension. Okay. But just remember, first the monolayer is formed. So using this, you can have the name of the instrument is QuantaSorb, and the detector will be thermal conductivity detector. The data you get can be put into this equation, which is the BET equation, Brunner, Emmett and Teller. Very important, Brunner, Emmett, Teller. Very rarely the question is asked on the direct equation. You can get the equation and you have to write down, find the name of the equation. You will get the name of the equation, find out the expression of the equation, right? Then we had the air permeability method. This air permeability method is based on the rate at which gas or the air is going to permeate through the heap or the bed of the powder, which is packed in the capillaries. Okay, this is done using the 𝙂𝙂𝙎𝙬 equation. It is the modified version of the 𝙂𝙂 equation only. You can see here it is, I think, little bit mistake in the expression. So this eta, you can see this is the velocity, this is the area, then we have the viscosity, pressure. This eta, definitely it is going to be the porosity, because the powders are packed in a way that estimation of the porosity, void volume will also be done. It is done using Fisher-Subsieve sizer instrument and water manometer. So by now we know methods of the particle size determination. Microscopy method one is there. Then we have seen the other one as the sedimentation method, sieving method, Coulter-Coulter method. Then surface area determination method, adsorption method and air permeability method. BET equation, 𝙂𝙂𝙎𝙬 equation. Volume of the solute or gas adsorbed. Here we have rate at which gas passes through the bed of the powder packed in the capillaries. Then we have QuantaSorb instrument. Here we have Fisher-Subsieve sizer. Okay. I hope now you can spot the equations well. Here you just need to put eta cube 1 up minus eta square, right? This E is the porosity, right? A is the cross sectional area of the bed. This SW is the surface area, right, of the powder. This eta is the viscosity. Delta P is the change in the pressure. T is the time. K is the constant. L is the length, and this is the E is the porosity. Then we have the BET equation here, where we can spot the vapor pressure equation as well as the volume of the gas that is used. Okay, just try to remember this equation. Nothing that they are going to ask or give you the equation to solve. Just the expression of the equation is very, very important. Okay, let's see now. Last we have is the flow properties of the powder. For today, because although there are density and porosity concept is also pending, but this is one among the most important. After particle size, surface area, we have is the powder flow properties. Because in pharmaceutics, while you are designing any dosage form, while you are designing any, thinking of making any tablet formulation or any formulation using powders, if their flow is not good, if their flow property is poor, definitely it is going to impact their final behavior. What final behavior am I talking about? Just now told you: dissolution, absorption, release, action, right? Then final outcome, the efficacy will be improved or not from comparison from the traditionally approved dosage form. So everything revolves around the powder flow property, for which you can determine it using some direct methods or indirect methods, right? So number one of which is the Carr's index. Very important, very, very important. GPAT last 5 years continuous questions are being asked on the flow properties. Your powder must have good flow properties. If by any chance your powder acquires any moisture, it acquires anything, it absorbs any solvent around, or cross contamination is there, it becomes deliquescent, it gets spoiled. That spoilage is going to destroy your final formulation. So that is why there is a good importance of controlling the and evaluating the powder flow properties. Number one is the Carr's index method. Carr's index method is nothing but based on the determination of tap density minus bulk density upon tap density into 100. Let's see how you get these tap density and bulk density. We have few minutes before we turn it off. So just as I've mentioned, we have Carr's index method. Carr's index method or compressibility index. Compressibility index. So in the Carr's index method, we have tap density minus bulk density upon tap density into 100. What is this tap density? What is this bulk density? So from the name, bulk, tap, let's see, most of you should have understood this by now if you have done this practical in your labs. Suppose if I give you a powder, it weighs 40 grams. Now you put this powder in a measuring cylinder and you get a volume here of 20 ml. You can spot the volume as 20 ml. So here the bulk density is nothing but mass upon bulk volume. Mass of the powder I gave you was 40, volume you spotted that it is 20 ml. So you got the bulk density as 2. Okay. Then we have tap density calculation. You have the same beaker, same powder, same weight, right? So you are going to tap it. You are going to tap it like this. So tapping is going to do what? It is going to minimize the voids. It is going to minimize the pores in the powder packing. So now the final you get, suppose, is the 10 ml. Right. So what is tap density? It will be mass upon tapped volume. Mass is same 40, tapped volume will be 10. So you get the final answer as 4. Right. So calculating the Car's index will be nothing but 4 minus 2 upon 4 into 100. It will be 2 upon 4 into 100, 425. So you get a Car's index of 50. So that is how the calculations simply are done. But only my here concern is we should understand what is this tap density, what is this bulk density. So Car's index is nothing compressibility index, which gives the nature of the powder flow, tap density minus bulk density upon tap density into 100, right? This was asked in GPAT 2025, just the formula. Okay, then for the tap density you have mass upon tapped volume. For the bulk density you have mass upon bulk volume. Okay, then you have second is the Hausner ratio. Hausner ratio is also another method for evaluation of the powder flow property, but it says it is nothing but tap density minus bulk density. Tap density minus bulk density. Okay, Car's index was tap minus bulk upon tap into 100. Hausner ratio is tap upon bulk. Okay, third and final method we have is the angle of repose. Angle of repose, right? So angle of repose is nothing but theta is equals to tan inverse h by r. Theta is equals to tan inverse h by r. What is this h? What is this r? Suppose if you have powder, this is a funnel, right? You add the powder into the funnel, it will form a heap down, right? It will form a powder heap. So what you can do, using your scale, you can get the idea of the height of the heap, you can get the idea of the radius of the heap of the powder. So once you calculate this height and radius, you put it into this equation, you get the angle of repose. So just like Car's index, which is tap minus bulk upon tap into 100, just like Hausner ratio, tap upon bulk, we have angle of repose. Theta is equals to tan inverse h by r. So as the value of the Car's index, Hausner ratio or angle of repose increases, the powder flow turns into poorer, like extremely poorer. So if the values are lesser, you get a better flow. Let's see what are these values, and we are going to complete this topic today. So number 1, you can already see Car's index or the compressibility index as tap minus bulk upon tap into 100, right? If the value is less than 10, if the value is less than equal to 10, you already know what is, how you are going to remember this. See, we say we are 10 on 10, right? So whatever is 10 on 10 is excellent. If I am getting 10 on 10, that means I am an excellent student. So 10 on 10 is going to be the excellent flow character, right? After that, there is a gap of 4, 4 and 5, 5. 11 to 15, 4. It is going to offer a good flow. 16 to 20, it is going to offer fair. 21 to 25, passable. 26 to 31, poor. Then 32 to 37, very poor. Greater than 38, very, very poor. Simple ways to find out excellent, less than 10, good will be plus 4, 11 to 15, plus 4, 16 to 20, plus 4 in between these 4, then 26 to 31, almost 5, then 5, right? So this way you will remember how you are going to see these equations, how you are going to remember which value holds what kind of powder flow, right? So whatever we find out was the, I think 50 value we had find out, it will offer a very, very poor particle powder flow. Then for the Hausner ratio is nothing but tap density minus bulk density. If the value is going to between 1 to 1.1, it will offer excellent flow. If 1.12 to 1.18, good flow. 1.19 to 1.125, it will offer fair. 1.26 to 1.34, passable. 1.35 to 1.45, poor. 1.46 to 1.59, very poor. And greater than 1.6 will be extremely poor. So how you are going to remember this? See, you just need to see the difference between these, right? For example, in this case, if there is a difference of 0.06. Here also the difference is around 0.06. Here also the difference is around 0.06 or let's say 7, right? Then so you can see the difference is around 0.05 to 0.09 only, right? So you can get an idea that the value of the 𝙂𝙀 ratio, suppose it is given to be 1.27. Let's suppose I give you the value of the 𝙂𝙀 ratio as 1.27. Tell me what is going to be the type of flow. Poor, good, passable, excellent. So 1.27 falls in the range of 1.26 to 1.34. It will offer the passable flow. Let's suppose I give you the value of Carr's index as 15. What will be the powder flow? So 15 will come under the good flow character. Okay. So that's how direct questions can be asked. Then angle of repose, we have seen there are two methods in the angle of repose. One is the fixed method, other ones include the rotating methods. You can see fixed cone method. That means the funnel that you are using is fixed, right? Only the powder that you are adding is going to come out. The ones that have rotating methods, for example, a rotating drum method, the drum is going to rotate. That means the instrument, whatever you are using, will rotate. Okay, here the instrument, the cone, the funnel is going to be fixed. That is just the difference. Tilted table method. We have other methods also. This one includes the fixed cone method, which we have covered like this. Okay, and the powder heap was formed. Then we have a rotating drum method, rotating table method. So just when the powder is going to slip here, this will indicate the angle of repose. So either the instrument is going to move or it is going to be fixed. If the value is less than 25, it will offer excellent flow. 25 to 30, it will flow good flow. 30 to 40, moderate, and greater than 40 will be poor. Okay. So that's it for today. I hope you all have enjoyed today's class. You all have learned so far and I have made everything clear to you all. Right? Thank you so much. We will definitely meet in the upcoming classes. You all need to mention in the comments below what exactly, what topics you would like to cover, if you would like to cover or not, and you are enjoying our series also. I would personally like to read all of your comments after the class. Thank you so much. We will surely meet very soon.